Do one more physics drill today. It's just going to be a multiple choice quiz, and I got some questions here already from a bunch of topics. The first question is: bead slides without friction on a rigid. Sorry, move this real quick. A rigid vertical circular hoop of radius r rotates with constant angular speed. So rigid vertical circular hoop. It's like this, radius r, rotates with constant angular speed w, linearizing about stable equilibrium. What is the small oscillation frequency? This isn't really something I can solve in my head. Bead slides without friction on a rigid vertical. What is the small oscillation frequency? So usually it'd be like G divided by L, but since we are rotating, I'm gonna go with B here. Like maybe we're adjusting the usual oscillation frequency by this W squared. To see. Charged particle enters a region of uniform cross fields, E, B, with initial velocity y, v naught. For which condition does the particle continue undeflected? Well, E divided by B has to equal V, I hope. It's either A or B here, and I can't really remember exactly which one it is. But I guess we'll just go with A, E over B. I don't have like a specific rule that tells me which one it is. I think E is on top though. For a particle in central potential, which quantity is strictly conserved? Which quantity is strictly conserved? That would be angular momentum. And that would be B. Oscillations. Two identical masses M are connected by three springs, each of constant K. Alrighty. What is the higher normal low frequency? It should be 3K for M, I believe. Which Lagrangian yields the Birkestoff curve for fastest descent under gravity? Um, I think it is this one because we have to do a variation in terms of the action where we're tracing a ds. So I'm pretty sure that it's going to be C here because that looks like the action into that looks like the action right there. Which identity is always true for sufficiently smooth fields? Should be del cross F equals 0? Maybe not. Um, Could be this first one. Oh my god, I don't even know what's happening in this question, but I'm going to go with A because I think that's the right vector identity. Because this will make a vector, this will dot that vector, and assuming there's only one direction in the vector, I don't know. Honestly, I don't know about that one. In electrostatic equilibrium, what statement about a conductor is correct? It may exist inside. No. Surface charge density must be uniform. Yes. Maybe. Potential is constant throughout the conductor. Yes. If, well, maybe. These are like maybes. Volume charge density may be non-zero. Man, volume charge density may be non-zero. No, I don't think so. I don't think there can be any charges inside the conductor. So I'm pretty sure that it forces a charge density on the surface, but I don't think it has to be uniform. I think the point is the charges move around to sort of force everything inside. I'm going to go with C on this one. Potential is constant throughout the conductor. In spherical coordinates with azimuthal symmetry, the angular equation yields which class of solutions? Finite. Well, those are Legendre polynomials. P L cosine something. C. For a localized charge distribution with a total charge 0 and dipole moment 0, localized charge distribution. Total charge is 0, dipole moment 0. What is a leading far field potential dependence? Right. Um, the dipole moment is 0. The total charge is 0. You know what? It's probably D. It's probably the quadruplet, this octuplet. I just have a feeling, but I mean the total charge is 0, so it can't be just monopole. The dipole moment is 0, so it can't be the dipole. And if you have r to the third, then you're implying that you're multiplying both of these two together. It's not going to work. But if you have 4 little charges, that might work. I don't know. We'll have to see. So which Maxwell equation in matter directly involves the displacement field? So Maxwell Ampere law. Or wait, what? Pretty sure that's for surface charges? No, that's definitely B. Yeah, B is correct. They gave me some answer key here. But I'm gonna see what they say here. So we missed 2 of them only. That's nice. I don't know how I was able to get everything right. I mean, this is something you kind of just have to solve a bunch of times. Or remember this exact shape here. So it's a bummer I didn't get that one, but it is what it is. Multiple expansion. This one here. Well, I guess this is the first non-zero term, so okay then. Maybe that's the correct answer. Alright. Try the next 10 questions, and then after that, we'll probably have to call it a day. Okay, so a particle at rest in a frame rotating at constant angular velocity. Forces must appear. I think central forces, centrifugal forces, and Coriolis forces. I think it's that. I don't know what order forces are. Two identical masses m, one moving at speed v, elastically collides head-on with another initially at rest. What are the final speeds? Well, the initial momentum is mv in extraction. Elastically collides. So we're going to probably get mv on the right side. How could that be possible if there's two masses? Probably have to divide them by 2. So you get mv divided by 2 plus mv divided by 2. Makes sense that it would be that. For a particle in a potential, the virial theorem, well, I don't know what the virial theorem is, but it sounds like it might be an average. I guess we have to go. These two answers are the same, B and C, which makes me think it might actually be one of those. Which potential yields closed orbits for all bound motions? Entirely sure. These are really hard questions. Air-trans theorem. For n equal masses connected by identical springs in a ring, periodic boundary, how many zero frequency modes exist? What? Yeah, I mean, this is either 0 or n. And I did a report on this actually, frequencies in a ring. I'm gonna have to probably go with n. Which identity is correct? That's gonna be C, unless they're trying to trick us somehow. IJK, IMN, JN, KN, JN, KN. Okay. Which charge distribution produces zero electric field everywhere outside the charge region? Spherically symmetric distribution with total charge 0. I mean, uh, inside a conductive region with full spherical symmetry, Laplace's equation permits which radial dependence? The spherical symmetry. Well, C. free region. Okay, so point charge Q is a distance E from an infinite grounded conducting plane. What is the magnitude of the force on Q? F equals Q E. Um, basically there's an image charge that is 2D away. So 2D squared is on the bottom, like 4D squared essentially is on the bottom. So it's going to be A. Bound volume charge density satisfies negative del dot P. And here we go. So let's see if I have these. Got a bunch wrong here. What? Velocities just swapped. Okay, that's definitely something I might want to like put in, say, physics 1.3, saying that moving in one direction, resting, that means that V2 or V final, or how can we put this? V1 comes in this way. The F equals V1. Okay, I have an idea. So if we have a V naught, then we have VF2, or sorry, VF1 equals 0, and VF2 equals V naught. If the other one is resting, then we get this situation happening. Boom. Okay. Bertrand's theorem. Only two central potentials guarantee closed orbits for all bounded motions. Oh, okay. I think this is a mechanics issue. Has to deal with something like this. So here's Bertrand, bounded what? Closed orbits. Okay, so we have V equals negative K over R, or V equals KR squared. this. Guaranteed closed orbits. What closed orbits are, but good enough. Ring of normal modes. Periodic chain has one translational zero mode. Okay. Well, that was enough questions for today. Hopefully that was helpful.